Hi, welcome to today's webinar. It's titled Apply Operation Science to Accelerate Success Now. I'm your host and moderator, Mark Graben, a senior advisor with KaiNexus, and I'm really excited that we are joined today by our presenter, Ed Pound, and you're going to learn more about Ed in a minute. So thank you, everybody, for being here, and thanks in advance to Ed for the presentation. Actually, if this is your first time attending one of our KaiNexus webinars, we welcome you. If you attend regularly, welcome back. Hopefully, if you don't know about KaiNexus, you might be curious to go check out our website, kainexus.com. In brief, we are a software company whose mission and passion is to spread continuous improvement. So if you'd like to learn about our software solutions and how we help organizations in all sorts of industries, you can visit our website at kainexus.com. So before we start, let me introduce our presenter today. Again, his name is Ed Pound. Ed is the managing director of the Operations Science Institute. He's the lead author of the book Factory Physics for Managers and is co-author of an upcoming book titled Applied Operations Science. Ed has over 35 years experience managing, coaching, and training in operations across many different industries and different countries and in businesses large and small. He has a bachelor's and master's of science degrees in mechanical engineering from the University of Alabama, and he also has an MBA and an MS in engineering management from Northwestern University. So with that, Ed, I will turn things over to you. Thanks again.
Thank you, Mark, and welcome everybody. Thanks for joining us today. So we're going to talk about operations science, and as Mark mentioned, we do a lot of training and coaching at the Operations Science Institute, but more on that later. The point is applying operations science to get results now with the people who are doing the work now. And here's the website. You can go to the website. You might say, Ed, you didn't give me the address for the website on this screen, but don't worry, it's on every slide, so you can't miss it. Okay, this is actually the first time we've made this public, but we're starting some online courses in operations science. I've had a lot of people over the years ask me, how do I become, more expert in operations science other than just reading a book? So the online courses should be launching around the end of March. We're actually going to offer 3 certificates. That was some of the feedback we got from the early look at the material, is people will want certificates. There will be a lot of concepts, but there's also going to be math and science, because that's where really the power is, taking that and applying it to your operations. And then at the end of each course, you'll do an evaluation, because this is not going to be something where you just go through, oh, I watched the video, so now I get a certificate. You actually have to work through some evaluations to cement that knowledge. And then, of course, it's the age of AI. So we're going to have an AI chatbot assistant, not to be left behind. The certificates that we're going to offer are flow leadership, inventory leadership, and we're going to do an operations science leadership, which is basically a combination of the two, aka operations scientist. So there'll be a lot more information about that coming out. You can follow on the website, sign up an account, follow us also on LinkedIn. Okay, so we said today on this website, this webinar description, that we're going to talk about a fundamental problem. And you might think, oh, what is that problem? I don't have optimal labor utilization. I don't have the optimal batch sizes. It's actually more fundamental than that. And this is an imperfect description, but this is one way to think about it. Basically, there's a knowledge gap in operations. And this is operations across every industry. On one hand of the gap, you have either very complex or technical solutions. And so, for instance, you'd go hire an academic. There's nothing wrong with academics. I love academics. But the issue is they get paid for publishing and they get grants for publishing and researching things that nobody's ever thought of before, right? And so you could have a optimization, multivariate optimization of multi-echelon inventory network, right? And so that's great. But giving that to somebody who's out on the plant floor, and if you're a leader trying to develop your organization, you're not going to hand that to somebody and say, go use that. I would actually put Six Sigma a little bit in that category, because Six Sigma statistics are very powerful, but there's a lot of statistics and it can get very technical. So that's one side of the gap. The other side is there the focus on best practice solutions. So, for instance, I would put lean in that category. The way lean got started was Rather and Shook went to Japan, looked at what Toyota was doing. They called that lean manufacturing. And then, boom, everybody says, okay, how do I become like Toyota? Well, there's an article, a lot of articles, but there's one on our blog site that talks about the science of lean manufacturing. And on the Toyota website, it says the Toyota production system, which was the genesis of lean, was developed over 40 years through trial and error. So trial and error is not probably the preferred way to get results quickly. Another example of that is agile and software development. Agile is basically just a list of principles, if you look at the Agile Manifesto, of the way people should approach software development. And actually, another one that I would put in here, which seems a little bit odd, the best practices is digital technology. You say, well, wait a minute, Ed, that's highly complex, that's highly technical. Indeed, it is. But what happens is people say, oh, well, digital, yeah, we should have digital. Let's everybody get digitally connected because that just seems like the good thing to do. And that's best practice. But that begs the question, why are you using digital technology? Where would it be most effective? So this fundamental problem that I'm seeing, and we're going to do a quick test here shortly and show you the results of tests we've done with basically thousands of people. The fundamental problem is there's this gap in understanding of basic concepts, operations science. And we're going to talk about that in this presentation. Now, the book that we gave away is called Factory Physics for Managers. And there's been an evolution from factory physics to operations science. And you say, well, why is that? Well, because we used to go into factories. I worked for Factory Physics Inc. for 16 years. We were doing consulting and software, and we go anywhere you went that wasn't a factory. Say if you went to a hospital, you went to an emergency department, you go to aviation maintenance and repair, aviation maintenance, repair, and overhaul, MRO, and they say, we're not a factory. And, that's a fair statement. The other thing is factory physics sounds pretty cool. Physics sounds really cool, but people say, oh, that's really hard. So I'm not sure that I actually want to get into the physics thing. So the term operations science is become a very good description of the general applicability of these concepts. Everybody has operations, whether you're in a hospital emergency department, whether you're in an automobile dealership, whether you're in a traditional factory, you have operations. And then, of course, people trust science. They trust the idea that, okay, you're using science. It's an objective solution. So that's how we got from factory physics to operations science. And about 2 years ago, I started the Operations Science Institute to carry these concepts forward. So what is operations science? Well, here's a quick definition. It's the study of the transformation of resources to create and distribute goods and services. That's pretty general, but remember, this applies everywhere, so it has to be general. And it focuses on this interaction between demand and transformation, or demand and supply, and variability in either or both. And so you're trying to figure out what's the best way to manage variability, because everybody has variability. And the real power and the solution to that fundamental problem is you can train everybody in your organization on operations science. Obviously, some people need to have more detail than others, but once everybody's aligned on that, the people that do the work can really turn that knowledge and their experience on their processes and systems to optimize those. So the basic element in operations science is an operation. What does that look like? Well, I have WIP and I have a queue. I've got transformation, which is resources that use time. I've got demand. I've got stocks, which is inventory waiting for demand. And then, of course, you don't have to be an operation where you have finished goods inventory. I'll keep coming back to the medical example, because that's just a standard example. Wait, I'm sorry, my animation's getting ahead of me here. So let's do some quick definitions. Work in process, queues, and transformation. So the main thing about this is you can read these at your leisure, but the main thing is work in process can be physical or virtual. That's a very, very important distinction. It could be code that I have to create to make a program. And of course, it could be something physical like a pipe spool that I have to install for a refinery. A stock, as I mentioned before, is a set of completed entities that's waiting for demand. Okay, and that's measured in units. Demand is this desire for an external cut from an external customer for whatever the entity or set of entities, which could be something physical or virtual. It could be a service. Now, the thing to remember is that transformation is measured in a rate and demand is measured in a rate because transformation synchronizes to meet demand. So that's a little bit of the nitty gritty. Mark, I know you've had some experience. What's been the reaction of people when in the medical industry, healthcare industry, when you bring up these concepts?
Well, even though I'm generally not using the phrase factory physics, any reference to factories does trigger, that reaction, which is a fact of people saying, well, we're not a factory. So
Right.
trying to get past that hurdle around transferable lessons, I certainly recognize that. But there are certain universal laws of physics, laws of operations that are applicable. And I know you're going to touch on this, but I think the one cause of many flow problems in healthcare is the desire or the reality of 100% utilization, because
Right.
people think it's wasteful to have rooms, equipment, people being unutilized or underutilized when that desire for 100% utilization actually cause a lot of problems that are also not well, yeah, they're not real desirable side effects of some of those policy decisions that really emphasize 100% utilization.
Yeah, absolutely. And you know what? That's an excellent point. And I'll give you my rating scale for points. An excellent point is one that I have a slide for. A good point is one that I can actually comment on intelligently. And an interesting point is one that I'll get back to you on. But that was an excellent point. We're going to talk about that specifically.
Yeah.
I want to give some examples here real quickly about how these concepts apply universally, because it wouldn't be very good science if it didn't apply universally. So, and we've actually done work in an emergency department, but if you look at it, patients basically are what show up at a hospital. And then I have resources, transformation, and transformation like could be registration, triage, treatment, which includes diagnosis, discharge, and then patients are either from the emergency department discharged to go home or discharged into the hospital. Okay, there's anybody who's ever been to an emergency department knows there's lots of queues where you're waiting. You go in, you get triaged, and you come back and you wait for a doctor and you wait for results and all that sort of stuff. There are queues. Patients themselves are the work in process. And then you'll have supplies like syringes or bandages or whatever that are actually sitting there in stock waiting for demand from patients. So that's one particular industry. Here's another one, aviation maintenance, repair, and overhaul. I've done a lot of work here. What happens is you get an engine in that you take off of a jet airliner. It comes in. You don't really know what's wrong with it or if anything's wrong with it. It might be just a typical overhaul. And so you have to disassemble it. And there's a huge amount of variability here because sometimes you think you're coming in for a light repair. And then, for instance, you find corrosion on a turbine blade. So now it's turned into a heavy repair. So that's the work scope. Things get clean. Obviously, this is a very simple diagram. There's so much more complexity, but I'm just trying to demonstrate the concepts across different industries. And then they get repaired and then back into a stock ready for reassembly and testing. Project management and construction. And all construction, you do basically these four things. You design something, you make it using raw materials, you transport it to where it needs to be assembled, and then you build it, and then you get a structure. The big thing people say in construction is like, oh, we're just building one building. This is not a factory. Yeah, but for instance, if you're building a refinery, you might be building 2,000 pipe spools, which are basically configurations of pipes that connect everything. That's a very repeatable process and should be treated as such. Project management, uh, project management in general, but here's an example here. Engineering configure to order. I get a quote. I configure the product to the customer's requirements, do some engineering on that, and then release it to manufacturing. Okay. The work that's done between quote and release to manufacturing, there's no physical work there. You're all doing these tasks, but your tasks are your work in process. Oh, and I almost forgot. Traditional manufacturing. This is where people typically think it only applies, right? But this is, very typical. I get a raw material, say a casting, I turn it, I mill it, I inspect it, and I hand finish, and then it goes into finished goods. So hopefully that gives you a sense that the concepts that we're talking about apply everywhere. That's what good science does. So back to Mark's point about this whole idea about utilization and cycle time, we're going to do a little test here. Okay, but first we have to define what we're testing on. So have your pen and paper ready. And unfortunately, we can't collate everybody's or combine everybody's responses, but I'll show you what happens when we do. And I'm going to define cycle time or first process time. Now, these are the definitions we're using. We've been consistent with this ever since, factory physics was published back in 1995. Process time is the time to do work at one process center. Okay. So 2 hours at process center 1, 2.5, 1 hour, 3 hours, right? Cycle time, though, is the time to get through that routing, right? And so if the routing is to go from process center 1 to 2 to 3 to 4, the cycle time is the time to get through that entire routing. Okay. So what we're interested in is this relationship between the utilization of my resources and the time it takes to get through. So usually cycle time is much greater than the sum of process times. I actually am not a big fan of the whole value-added, non-value-added discussion because that's one of those sort of best practices things that can be highly subjective. But that being said, if you look at the value-added time, that's the whole that's the big takeaway there. Oh, the value-added time is so small compared to the overall cycle time, and there's a reason for that, right? And generally, it has to do with the amount of wait time required. So there's a whole lot of ways to quantify that other than having some subjective discussion about value-added time. All right, so we've defined process time and cycle time. Let's look at what utilization is. I think everybody's fairly familiar with this. If I have demand of 3 parts a day and then I'm working 1 8-hour shift, now I'm looking at utilization as the time used over the time available. Okay, so we're going to look at process center 1. The process time is 2 hours. I'm doing 3 parts a day. That means it takes me 6 hours to do that during my shift. I've got 8 hours a day. So my utilization there is 75%. Okay, pretty straightforward. Okay, so you would think because people are working with this concept day in and day out, you even use it at home, right? Now you look at your schedule. What do I have planned for today? How much time do I have to get it done? What does my wife have planned for me today? How much time do I have to get it done? It's just something that should be second nature. And it's kind of like what happens if, I've got a ball in my hand. I don't have a ball with me, but imagine I do. And I let go of it. Everybody understands intuitively what gravity does, okay? How that science works. So we would think that we would have that same intuitive understanding about this relationship between cycle time and utilization. So here's the test. We've done this test with literally thousands of people. And so when you're at home and you only get like 15 seconds, because again, you work with this stuff all the time, should be just as easy as drawing the path of a ball that rolls off the table. Take 15 seconds and draw this relationship. Okay. So we've done this, as I said, thousands of people, and typically it works like this. Okay. You see those little blue Post-its on the table, you hand those out, you get a crowd. And these are not people, who work in parks and recreation. These are people who have combined hundreds of years of experience in operations. You say, okay, draw that relationship. What's the relationship between utilization and cycle time? And then you combine the responses, and that's what you get. It looks like this a little bit more up close, but basically it's a spaghetti diagram. So the takeaway there, this is the fundamental problem that I'm referring to, is that you have this issue where you have wildly varying understandings of this basic relationship. Some people think that as utilization goes up, increases, cycle time goes down. Others think it's the other way. There's just a huge variation. And this be like asking somebody, hey, I wonder what happens if I go to the top of a 5-story building and step off, right? And so that's the fundamental problem. And it's as much the fact that there's varied understanding as that some people have the wrong understanding. I mean, it's important for people to have the correct understanding, which we're going to show you shortly. And there's actually math and science behind that. But the fact that people have different understandings causes almost as much trouble, because if you're a leader in an organization and you're trying to get everybody to pull in the same direction, and people's understanding are like you see here on the slide, you've already got a very fundamental problem that you're dealing with. And people might be working to the best of their ability and they have good intentions, but they just have the wrong understanding. And one time we did this and somebody said, oh, yeah, Ed, but like 60% of these people got that right. I'm like, well, that's better than 10%. Mm-hmm. But imagine you're on a crew boat, and you're rowing and it's a 10-person crew boat and 6 of the people are pulling in the right direction. And then the other 4 people are just, rowing wherever. Mm-hmm. The point is having that unified understanding really clarifies focus. It's hard to overemphasize how important that is.
Yeah.
Yes, sir.
Just to interject real quick, Ed, and especially for those who are maybe just listening to the podcast recording and don't have the visual in front of them. As you pointed out, Ed, there are some people who said they think cycle time decreases as utilization goes up. There are some who drew a curve where cycle time is increasing as utilization goes up. But that's also interesting to see. Some people think it's a linear relationship. Some people draw a curve that's more of an exponential curve. It looks like some people have drawn what you might call an S curve. Yep. So that's an interesting variation as well. Not just the direction, but the shape of that relationship. Yes.
Absolutely. Absolutely. And it's just amazing the results you see, again, as leaders trying to manage organizational development when everybody gets on the same page. And I'll just give you an anecdote. When we were doing these training sessions at a client, and these people were training, we did people who had been there for a long time, combined with people who had just started, managers, engineers, line techs, whoever. After the training, we were doing a couple of sessions and talked to one of the guys who had been to an earlier training session. He goes, yeah, we used to think that we had 30 problems and 30 potential solutions because we had 30 people. Since we've been through this and we have the framework, what we've realized is we have 4 problems and we are dead set focused on those problems. And so that alone in and of itself, which is why I emphasize this idea of having a common understanding, really reduces unnecessary stress and chaos, which is a great benefit to understanding the science. So there's actually a mathematical relationship that answers that question. It's called the Kingman equation. We call it the Butt equation just because that's the MBA version of it, right? There's a variability component, and C sub A squared is squared coefficient of variation of arrivals. C sub E squared is squared coefficient of variation of effective process time. I'm not going to go into that detail. There's plenty more to explore behind that if you'd like. There's a U component. That's utilization. That little u is the time used over time available that we showed that quick example where we calculated 75% utilization. And then there's a T factor. which is the process time, and it's the process time for a batch, not for a single piece. So if you look at that relationship, here's what the curve looks like. Now, you notice there's a couple of things going on here. There's a curve at low variability, and there's a curve at high variability. So that's another insight that is not something that you need to pull out a slide rule and calculate. It's like, oh, I got a lot of variability. Boy, my cycle times are going to jump up a lot more quickly than if everything was just kind of lockstep and I was making salt shakers or something like that all day long. So that's the relationship. Now, there's a company called Conax Technologies. Bill Furley, who's a good friend and also on the board of advisors, they are sort of an engineer to order, configure to order engineering company. They make compression seal fittings. They make temperature sensors and cable and wiring harnesses, right? So they don't have they're not making stuff thousands and thousands of the same thing. They're making small lots, and they apply this in practice too. And here's how they apply it. They've got a situation where they have resources, say process centers that have low variability and high variability. So how are they going to manage those to get the kind of performance that they need? If they're looking at trying to maintain a 3-week lead time, and they're looking at their plasma welders, this is a machine, it's not a person. The plasma welders, man, they just had a terrible time trying to dial those things in. They've been working on them for years and years, but the variability is just very high with that particular operation. So knowing that, when they plan, they set their utilization, because it's high variability, at about a 52% rate. Now, if we got any accountants in the audience, they might be, having a heart attack now. Got to grab her, right? 52% utilization. But if you're going to be predictable, that's just the way that process works. Now, you might want to spend $5 million to get a more dependable machine if one exists, but you can make that trade-off once you understand this. And then they have a mill, the Akuma mill, right? Very dependable, right? They churn things out on that part, not a problem. So the utilization plan utilization there is 92%. And in any case, by understanding this relationship and planning for that variability, because you can wish the world was one way, and or you can plan for the way the world is. That's the way they're able to maintain the 3-week lead time that they're looking for. So that's just
sorry,
yes,
I'm sorry to interject once more, but
Please
just
do.
to talk through this curve for those who are just listening. The correct answer to what Ed was posing and asking different people to draw out earlier is that cycle time increases as utilization goes up. And if we look at that low variability curve, cycle time increases very slowly, almost linearly, until it starts increasing, with a curve upward. And when it hits about 95%, it really skyrockets. And I've heard that described. Correct me if my recollection from factory physics is wrong, but you could call that a cycle time explosion.
Sure. Yep.
And then with the high variation, that curve is increasing more quickly from the get-go, and it still has that big explosion uptick that happens more like roughly 75% utilization, just to talk that through for people who are just listening.
Yeah, thank you for doing that. I tend to run through it too quickly. I'm glad you slowed me down on that one. So yeah, it's a fundamental relationship. And the other thing is, for managers and leaders, what's the worst thing you can see, right? Oh, I got these people sitting around. But, that's just a capacity buffer, right? And that's a way to address variability. I was talking with a guy just yesterday, and he's like, well, one of the things we want to do is reduce our labor costs. We want to automate everything. And he had read the book, and so he's like, but I'm wondering if we do that, because we have a lot of variability, we still might have to have all the people, because they're very flexible and they can flex from one line or one machine to another to address that variability. So the fact that people are sitting around, I'm not suggesting that they sit around, and play tiddlywinks. There's other things they can be doing, right? But they don't necessarily have to be occupied working 100% of the time. That's just a recipe for disaster. And that goes on actually in construction. That's a terrible problem because in construction, they really hate for people to be sitting around. They want material waiting on work. They don't want workers waiting on material, which is a whole another discussion. But yeah, so that's a fundamental relationship. And that's just one part of this fundamental problem that I described, because there's a lot of relationships in operation science that help you get your mind around this so that you can be predictable about managing variability. So we talked about cycle time. That curve basically was just for queue time. In other words, wait time, and it's an approximation, right? But it shows you the general behavior of cycle time and utilization. If I want to really look and dissect cycle time, I don't have to do a design experiment using, Six Sigma Taguchi methods, right? They're actually known, and here they are. So that's easy. We'll just move on. I'm sure you got that. But no, they're labeled. There's process time, setup time, downtime, queue time, batch time, wait to match time, move time, shift differential time, and planned time buffer, which is actually specific usually to construction. The point is, these things are all known and they can all be quantified. So when you're going to understand how your operations behave, use the science and math to understand the various components. On the website, we have a glossary that you can download if you go under resources and articles. It requires a free account. We won't spam you if you want. You can opt out of emails, but that resource is there to talk more about these terms. The other thing to think about is understanding the science of understanding my processes versus these best practices that we have. The issue is, say, Six Sigma, and look, this is my view on it. I'm sure people would argue like, oh no, it works on wait to match time too. The general illustration here is Six Sigma focuses on process time, downtime, and queue time. Lean looks at setup times, queue times, and move times. And then Agile, really, here's the whole thing about Agile. When you set a sprint size or sprint length, what you've set is the batch size of work for your production process when you're doing software coding. So it's not that those are bad. Don't ever quote me and say, oh, Ed says lean sucks. I'm not saying that. What I'm saying is these tools can be useful, but they're incomplete, particularly as most of them evolved as best practices. Somebody was doing something great somewhere else. So we want to see how that applies where we are. What happens is you have these knowledge gaps, and so things get sideways. And that's why you run into these things where people see like it's the program of the month. Here comes another program. Oh, we just have to believe. I can assure you when we go and we do training with groups, the whole veterans are just sitting back. They're like, oh my gosh, here we go. Here's another one. I know I can upset this apple cart because, it's just something else. I got to believe to make sure it works. And then when they're done, they're like, oh, wow, this, you didn't ask me to believe anything. You showed me how this works and you showed me the math. So it's very, very powerful in that regard. All right. So as we're drawing to a close here, we just make it kind of simple in terms of the implementation of operation science. 3 components: design, implement, and control. If you got a process map, that's where you start. If not, make a process map because you have to have that to get started to understand what you're modeling. And then you turn that into a model with some data and with these concepts. And then you can use that to do optimization of a new process. We've had companies who've done this and basically said, you have to do this analysis before I approve your capex expenditure to add a new line. Or you can look at your current process and see where there might be opportunities for improvement in the design as it is now, and then implement. But everybody goes straight to implement, right? Everybody loves implement. Let's go out, let's do something, let's move things around, we'll do a Kaizen. And then, how do you know the Kaizen that we did last week is not working against the Kaizen that you're doing this week? And then once you design and implement, you have to control it. if I do design perfectly and I do implementation perfectly, it can all be wasted if I'm not using the proper controls that correspond to the behavior of the operations as described by the science. So those three simple components are the way to think about how you might apply this in your particular organization. And you need to have all three, right? So the point is, there is this fundamental problem, right? And operations science really fills that gap and gives people the ability to fix things on their own. I mean, look, I used to be a consultant. I'm not saying consultants are bad. You know, they can be very helpful, but you don't need to go looking outside your organization. Typically, you can get a huge benefit with the software that you have. Even if you say to me, Ed, our software is Excel. I'm sure nobody out there would ever say that, but it happens, right? So what you want is a world where with this science, you've done practical optimization. That doesn't mean it's perfectly mathematically precise optimization, but it's the optimization that works for your business. And you can sustain that success. You know, once people have this knowledge, they don't try to reinvent the wheel, right? They can do this repeatedly over and over. And, you know, as you bring new people into the organization, make sure that they understand the science, because this provides that framework where you can clarify focus and unite efforts. And individually, it really helps people with the work that they're doing. I mean, it can be very gratifying because people want to do the job well, right? And now you've given them the knowledge. And so, you know, one guy said, nobody around here can ever tell me why we do what we do. And once he was done the training, he could understand that. So what you end up doing is managing variability predictably, right? That sounds like that doesn't make sense. It's variability. How do I manage it predictably? Well, you can't predict the future, right? You can't say what's going to happen next Friday at 3 p.m. But what you can do is select a range of variability, both in supply and in transformation. You can then set your resources, your buffers, capacity, inventory, or time to address that variability for a given, say, cycle time and a given on-time delivery, service level, and for a given cost. And so it becomes predictable. Now, if things go outside of that range that you plan for, you have to make a decision. Do I get less than I wanted with service level or cost, or more cost, less service level than I wanted? Or is this just a one-time thing that I just let it pass? And then finally, once people understand this and you get the unity and the focus of efforts, the stress and the firefighting really, really drops. And it's kind of hard, actually, if people are and love, you know, you got the cowboys who are out there and like, oh, I'm going to go expedite this part, or I'm going to go, you know, make sure that we get this service delivered as quickly as possible. This is different. That's not going on. It's not that you will never have that, but it's not something that's going to be the regular mode of operation. And so that's where you want to go. That's where operations science will take you. So that concludes the fixed portion of our program. Mark, it's all yours.
Hey, Ed, thank you so much for the presentation. And we're going to make some announcements and encourage people to continue putting questions in via the Q&A. So our next webinar in this KaiNexus Continuous Improvement webinar series is going to be held March 21st at our usual time, 1 o'clock Eastern. It's going to be presented by Tracy Defoe from the Learning Factor, Inc. The general topic, we still haven't decided what the exact focus of Tracy's session will be. At a high level, it's going to be about kata and continuous improvement. So registration is not open for that, but everybody who has registered for this webinar will receive an email in March when registration is open for that, or you can sign up to get notified of future webinars. If you're just watching the recording here, you can go to kainexus.com/webinars. So Tracy Defoe, March 21st, and the 100 plus webinars in our library over the years, you can find those at kainexus.com. click on the KaiNexus Webinars on Demand icon that you see on the right-hand side of that screen. Okay, next we want to invite you to visit our blog.kainexus.com. There's always a couple of articles on there every week about all things continuous improvement. Next, I want to tell you about our podcast, the KaiNexus Continuous Improvement Podcast. The audio of this webinar will be available there. The preview that Ed and I did a couple of weeks back, all sorts of great content in the podcast feed. You can subscribe basically anywhere you listen to the podcast, or you can go to kainexus.com/podcast. And then finally, last announcement, and I think this was a little small Kaizen that we did a couple of months back. After adding this appeal about filling out the survey, response rates more than tripled because your feedback does matter to us. I know a lot of times people get surveyed out and they think, oh, they're just asking, but they don't look. We do look at all of the responses. What went well? What could have been better? What topics do you want to have webinars about in the future? So if you're worried if we actually look, the answer is we do. And please do take a couple of minutes if you can to give that feedback. All right. And so with that, we're going to go through some Q&A. Ed's email address is on screen. The website for the Operations Science Institute is opscience.org. So I'll invite you to check that out. A lot of questions here, Ed, and a lot of conversation we can continue to have. When you talk about variability and some of your examples around manufacturing, what are some of the main causes of variability? Is that things like equipment downtime or quality problems, or even just variation in the processing time if it sometimes took more than 2 hours? Can you kind of elaborate on those causes of variation?
Sure. There's two, keeping it simple, there's like two areas you look at variability. There's demand variability. And if you're an operation, say if I'm in that MRO facility and I'm the plasma spray shop that receives something, I can't really control my demand, right? And so the variability, the demand variability is really the variability of arrival times between arrivals, right? So, but demand variability actually typically is the largest source of variability. But within transformation, now I'm in my resources, all the things that you named, absolutely, that's variability, like different processing times, even if nothing goes wrong, right? Sometimes it takes me, 5 minutes to do a particular operation. Sometimes it takes me 10, right? And understanding what you want to plan for, because that's the issue. You have to say what you're going to plan for. And the more variability you plan for, the more buffering is required. We didn't talk about that, but that's kind of a fundamental concept. Because I have variability and I'm trying to synchronize demand and transformation, I will have buffers. And the buffers there's an inventory time buffer and there's a capacity buffer. But all of those sources that you named, yes, process times, it's the way people do work. It is machine breakdowns. Those are all sources of variability. And the general concept is that if you're going to plan for more variability, you can be predictable about whatever level of variability you have in your organization. But if you plan for more variability, you're going to require more buffering. If you can reduce your variability, then you require less buffering.
Mm-hmm. So around buffering, I mean, I'm having a flashback to almost 30 years ago when I was at General Motors.
You were 5?
No. It's right out of college, but
Okay.
this was pre lean for GM, or at least for that plant, and I don't think they had a real good understanding of operations science, which was frustrating to me. I was fortunate to get to study that book, Factory Physics, even before it was published. But at GM, it was a high variation, high variability environment. Demand variation was very small, but machine downtime,
Right.
defects, scrap, rework, there was a lot of variability there. And maybe as a result, I mean, the mindset was buffer, inventory
Yeah.
buffers. More buffers were always more better.
Oh,
How,
yeah.
how would you have addressed that mindset? At some point, are there diminishing returns to more buffers?
Well, yeah, there are. I mean, basically, work in process inventory is a proxy for time. So if you see more, if you walk out on in any particular operation, you could walk into an emergency department. You see a bunch of people sitting around. Guess what? Your time to get through there is probably going to take a lot longer than it would have if you just walked into an empty emergency department. But the same thing with inventory in a plant, right? A lot of inventory sitting around, unless it's all scrap that the accountants don't want to write off the books yet.
That was a problem too.
Yeah, that's the problem. Then that's a lot of time. And so you can actually model that. There's some things you can do with operations science. And this actually was new science that Spearman and Hop came up with when they first published Factory Physics, and that we continue with operations science. You can create performance curves that show the relationship between the amount of work in process that you have in the system, the throughput you're going to get out, and the cycle time. And so in terms of looking at that mindset with people, because that's where the benefit is. You can tell people till you're blue in the face, but they'll see it when they believe it, right? And so how do you get them to believe that is you go through some of these concepts. There's some exercises that you can do. And a lot of times people will say in that particular situation, and we had this at a client, they had about, I'm going to say, 7 times the inventory that they needed for a particular operation. But their customer told them, okay, you can be sole source for us, but if you ever run out, we are going to qualify another supplier. So strategically, they were never going to get close to it. And so when we said, hey guys, okay, I get that, but you still have 7 times the amount of inventory you need. Why don't you cut it by whatever that is, 80%, right? Not 80%, 85%. Can't do the math in my head. But anyway, they're like, no, we're not doing that. We are absolutely not doing that. And so what you can do though, is you just walk it down, right? And you say, okay, well, let's walk it down again. So you get some confidence in the concepts that we're talking about in the math and the science. So getting people's minds around the concepts and how they apply it to what they do is a big challenge.
Okay, so here's an easy question before we get back into maybe the harder questions. When is that book, Applied Operations Science, going to launch?
Well, I don't know if that's an easy question, okay. Mark, but
all right.
I'm this year. I'm going to say beginning of the 4th quarter is what I'm thinking. Where we're going right now. We just got to get back on it. I've been working a lot on the online courses. Anyway, that's the short answer.
All right. There's all kinds of causes of cycle time and processing time in the production of a book.
Yeah. I have my own variability.
Lots of cues.
Yeah.
So, all right. So we have another question here about can operations science also manage job shops, or do you, in your online courses, teach the math in ways that's useful to simulate the flow of a job shop?
Oh, absolutely. I mean, yeah, like I said, if it didn't apply everywhere, it would be very good science. And actually, I gave the example a couple of times for maintenance, repair, and overhaul. Those places really are job shops. And they were one of the ones when we first started there, like, we're not a factory. We don't know what parts we're going to get. We don't know what repairs we're going to need. The big issue with job shops, typically, and actually I'm invested in a medical products job shop called ARC Industries. And in Factory Physics for Managers, Chapter 7 is all about how, if you look at that book, Chapter 7 is all about how the concepts are applied at ARC. Because what you want to do is you have this huge, in a job shop, you've got capital equipment invested. There's a big fixed cost there. You're carrying that. And then you want to make sure that you use that as effectively as possible. But yeah, absolutely, the concepts apply.
Okay, Edward, another question that came in here. How would you describe the difference or the connections between operations science and operations strategy?
Well, we actually talk about that in the overview courses. Um, business or organizational strategy are the actions plans that I set to achieve an organization's goals. Operations strategy now, because when I set my organization or my business strategy, I'm setting basically what customers I'm going to go out after, what products I'm going to offer, what channels I'm going to go through, how much I'm willing to spend in terms of resources to meet those goals. When I do that, I basically set the performance envelope, which I mentioned briefly before. And now the operations people come in and they have to decide what's the best configuration of their capacity inventory to meet to address that performance envelope and the variability associated with it. Right? If I offer more products, I'm going to go after more customers. That's more variability. But how to use those buffers to best meet that performance envelope that was set by the business strategy. So operation strategy is the design, implementation, and control of those buffers and variability to meet the organization strategy.
Yeah, I was thinking back, you've got some reminders on your popped up on your screen, Ed.
Oh, I did. Oops. Oh, get a haircut. Yeah.
That's why somebody in the chat said, don't forget your haircut.
Yeah. Thank you. Thank you. I appreciate that.
We'll call that a near miss. That could have been worse.
Yeah, that could have been a lot worse. Yeah, definitely.
But back to, operations strategy, you're making me think of something that was only more like 25 years ago instead of 30 years ago. When I worked at Dell Computer, they actually did a lot of really innovative things to try to manage demand. I think it's a rare example. You said earlier, Ed, something I think is very generally true that, you can't manage demand. But, Dell would do things looking at pricing and offering discounts on certain items to really try to match demand to supply. And I think it's a good example. They made a lot of mistakes, I think, that could be addressed by operations science. But I think that was a good example of, right or wrong, Dell's operations were pretty closely connected to operations strategy and sales strategy. And that was a little bit more off topic than I thought it was before I said it. But
no. Thanks for calling that out, because I want to clarify. Absolutely, it's called demand shaping, right? Mm-hmm. You can definitely decide what kind of products you're going to want, and you should do that, right? You absolutely should do that. But to do that and do demand shaping right so that you get the most cash flow out of your resources, you have to know how your resources behave. When I mentioned that you can't control your demand, that was for like an internal shop, right? But there are certainly other businesses, as you mentioned, Dell. It just depends on where you are in the process, right, as to whether or not you can control your demand.
Yeah,
and shape it.
So one other thing this is my question or reflection, looking for connections to lean and what you talked about, Ed. I think, to your point, there's a risk of somebody maybe misinterpreting lean and, let's say, the word waste. And they look and say, oh, machine downtime is waste. We're going to work on eliminating that and run everything up to 100%. Now, that would violate a lot of the principles and laws of operations science. It's going to cause problems like long lead time, which is not our goal with lean. We're generally trying to bring lead times down. So I think, being careful about that definition of waste is important. Otherwise, we might end up with the same sort of accounting driven decisions. And even going back to the books of Taiichi Ono, he would emphasize that idle people or idle machines is not the problem. Idle flow of the product through the system is the problem. So it seems like there's pretty high alignment around, core Toyota production system teaching and operation science. What would you say to all of that?
the whole thing about lean or whatever your initiative is that you have going on now, I would never tell you to get rid of that, right? Because
Mhm.
you've set it up for your company, you've got the vernacular, the language set up. You just want to make sure that you're not driving things and getting unintended consequences because you don't have a good understanding of operation science
Mhm.
and you don't have a unified understanding within your organization. You know, all you leaders out there, right? Everybody needs to understand this, and then they'll use whatever. That's the great thing about it is it's totally agnostic. You know, it just basically provides the foundation of the science to get whatever you're looking for. And on that issue with waste, yeah, I mean, I guess I wouldn't say that it, you know, having machines run at 100% availability or 100% utilization is violating the laws of operation science. I would just say that the laws of operation science will show you what's going to happen if you do that, right?
Right. Well, and there's a difference between a bottleneck operation that might have to run at 100% to meet demand versus trying to run everything at 100%,
Yes,
which is going to lead to
absolutely.
the buildup of all of that WIP. And
Yep, absolutely. Oh yeah, I mean, I remember going to a place and they had their lean effort and they were focused on the non-value added and they're like, oh, move time is non-value added. So they would just put everything in big, you know, totes so they
big
could
giant
move
batches.
everything as little as possible. But
Oh,
uh, what they were missing was the waste of capacity because they were having to run huge
yeah.
batches, right?
Yeah.
Anyway, so yeah,
Yeah. And
that's
the
a very
impact
rich
on
discussion.
on cycle time and
Yep,
customer deliveries. And, we don't want to push higher utilization because that in a lot of cases could be overproduction, which is really one of the, if you will, seven wastes,
sure.
classical seven wastes of TPS. It's not machine underutilization. It's the opposite of that, where the overproduction is called out as a problem. And then maybe the last thing we're going to have to wrap up here. I think the one alternative to overproduction is to use that extra non-productive time for continuous improvement.
Right.
When you were saying there's other
Absolutely.
things we can do with that time instead of
Yes.
twiddling their thumbs, let's work
Yes.
on reducing setup times and other things that can help improve flow and
Yep.
cycle time.
Absolutely. Yeah. So I guess over these decades, I've kind of come to my definition of optimal is you're getting maximum throughput. So you're meeting your demand with minimum cost. So that means minimum fixed cost, minimum variable cost invested in people, plant, and equipment, property, plant, and equipment. And you're doing it at whatever service level you choose, because you might, I mean, the salespeople will tell you, oh, I want 100% on time delivery every time, but that might be prohibitively expensive. And
Mhm.
so you're getting maximum throughput, minimum cycle time, and minimum cost, right?
Mhm.
Now, what does that mean for your business? Well, it's different from business to business, but the operation science can help you figure out what that is.
Yeah. Okay. Well, we are at the top of the hour. Ed, thank you so much for the presentation and the discussion. There are many, many thank yous in the chat. Again, we'll encourage people, please fill out the survey that will pop up at the end. And people asked about the slides. That PDF is available. There will be a link to those slides on the webinar recording page that we're going to email people about. So again, the session today, I want to thank our presenter, Ed Pound, Managing Director of the Operations Science Institute. You
It's a
can
pleasure.
email Ed, espound at opscience.org. And the website, of course, is www.opscience.org. Ed, any final words that you would like to share as a wrap up?
Just that the operation science, I've seen so much chaos and so much suffering caused by people not understanding this. And that's part of the mission of the Institute is whether it's me working with you, you learning through online courses or the books, put the science to work because it will really help you in your day-to-day work.
Well, Ed, thank you for that passion and that mission, and thank you for sharing everything with us here today. Thanks again.
My pleasure. Thanks.